Very welcome to everybody. Thank you for coming to this session. It's really heartening to see, at 3 p.m. such a full turnout. So really appreciate. And it's also very good to, finally have face-to-face events, live events again. So really appreciate all your attendance here today at this session. So good afternoon. My name is Tong Seng. Welcome to the session USE 301, titled Build Next Generation Applications with Event-Driven Architectures. So I'm a Senior Solutions Architect from AWS Public Sector, and joining me on stage today is Marcella Teng, Associate Solutions Architect from Asia Emerging Markets. Is there a clicker with you? Sorry about that. The clicker is on the... Yep, okay. Right, so I would like to begin this session by leaving everybody with a quote. This quote is from Mark Andreessen, who is the co-founder of Netscape and a tech venture capitalist. And he famously mentioned back in 2011 that software is eating the world. And the context in which this was shared was that many of the successful and fastest growing companies of the time are increasingly using software to power its daily operations and reinventing customer experiences and industries in really meaningful ways. So fast forward to today, we increasingly live in a volatile and change-driven world. Just think of the disruptors that's happened to us in the past couple of months, from soaring inflation rates to the Ukraine war, and also not to forget, we just came out of the COVID-19 pandemic. And in order to weather these changes, not just as a means to survive, but as a means to thrive, we need organizations and businesses to be much more nimble, agile, and innovative to solve problems. And as a consequence of how deeply embedded we are with technology, we need technology itself to be changed in much more rapid, frequent, and reliable fashion as well. So we have seen customers who are successful in these times tend to have a set of common practices. And the first of such practices is that of a DevOps practice. DevOps allows new applications and software to be rolled out in a much more frequent manner. And DevOps embraces concepts like continuous integration and development, which allows us to use highly automated workflows and testing steps to ensure that code changes are delivered in a way that minimizes risk. We have also seen customers change the way they are organized themselves and build themselves around small autonomous teams. These teams have end-to-end ownership of the entire service journey and break down traditional boundaries of design, development, and operations. These teams should be no larger than 10 to 12 people, where in Amazon, we call this a 2-pizza team. Basically, the number of people you can feed with 2 full-size pizzas. But what's important here is that these teams are empowered to make the necessary technology decisions that best drives the business outcomes. And this fosters an innovative and problem-solving mindset that is needed to be competitive. More importantly, at a technology architectural level, these teams have chosen to use a microservices architecture. A microservices architecture allows us to define an application in small, loosely coupled software components created with a single responsibility model. Having a microservices architecture fits very well with the practice of DevOps and CI and CD because code changes can be delivered in a much more independent manner. Because each microservice is decoupled from one another, changes to each service is low risk and reversible. A microservices architecture provides the necessary technology foundation for small autonomous teams to flourish. These teams are free to implement the necessary technology stack without fear of entangling or affecting other services. So I've mentioned the term coupling a couple of times by now, but what do I actually mean? So simply put, coupling is a degree of measure of independent variability between connected systems. How much can a system remain unchanged while dependent systems are changing? And to decouple takes conscious effort, both at design and runtime. And it's important to stress that there's always some degree of coupling between components that exist somehow. And it's our job as engineers and architects to constantly strive towards minimizing this as much as possible. There isn't just one form of coupling. In fact, it takes multiple forms. And to illustrate some of the effects of coupling more closely, let's use a transaction which is simple and relatable. So I'm sure in this post-pandemic world, many of us have accrued a lot of air miles waiting to be spent. And many of these are probably expiring really soon because we have earned them more than 2 years ago. So suppose you have our favorite airline website choosing to purchase and air tickets with miles. In order to do that, you need to know how much air miles you have and how much air miles you need to debit to get the ticket. So the ticketing service needs to fire off a request to a service that contains such data, and let's call that a customer service. So upon receiving that request, a customer service will query its database, runs its logic to ensure that the necessary miles that it needs to be debited is present, and proceeds to debit with the required miles. If it's successful, it will return a call back to the ticketing service, completing their part of the transaction. And the ticketing service can also then carry on with issuing the ticket, persisting that data to its local database, and returning back the response to its client. So you might think this is probably a very simple and innocent workflow. So let's dive into investigating some of the effects of coupling here. The first example is that of runtime coupling, right? Because the ticket service cannot respond to the customer service until the customer service has done the query and responded back. So this is quite undesirable for two reasons. First, it needs both the ticket service and the customer service to be available at the same time, and this creates two points of failure, reducing the availability. Two, it reduces the responsiveness of the application because the ticket service cannot proceed with other logic and is requiring the customer service to respond back first. The customer service could be overburdened by other queries and thereby affecting the performance of your application. In fact, a common anti-pattern is a brittle architecture that has many long chains of synchronous calls, and each service ends up being a single point of failure. So the second type of coupling I want to investigate is design time coupling. And because the ticket service consumes the API of the customer service, and there is a risk that changes to this interface will create the need for lockstep changes. Lockstep changes are undesirable because it requires both teams to coordinate effort and reduces the effectiveness of loosely coupled teams. And if we design our data persistence around a monolithic database, we might be exposed to some degree of infrastructure coupling. So when both tables, for example, are deployed from same infrastructure, there is a competition of resources and possibility of resource starvation. Not only that, there is a risk that a failure or misconfiguration of part of one service can make all services unavailable. So ideally, each service should have access to its own set of infrastructure resources that are independent and scalable. So to make this workflow more efficient, we should further reduce coupling between microservices. First, we should opt to adopt a communication model that is asynchronous and on the basis of events. This prevents runtime coupling from occurring, and each microservice can continue its operation at its own time and at its own target. There is no dependency for both to be operational at the same time, and this improves reliability of the system. Second, so long as we are communicating on the basis of an agreed event format, the way each microservice implements its logic is entirely no concern to other microservices. Changes to this implementation logic is also decoupled from other microservices as long as a minimum information is passed in the event. Thirdly, each database should also be individual to its respective microservice. This allows the database schema to be created in such a way that best suits the needs of the microservice itself and decouples resource sharing from other databases used by other microservices. In fact, this is what is known as a database per service pattern, and it allows different database technology to be used that better suits the needs of the data. For example, ticketing data stored could be relational in nature and be better suited with services like Amazon RDS and Amazon Aurora. Similarly, customer data could be organized in a series of key value pairs and be better suited by NoSQL databases such as Amazon DynamoDB. Changing this underlying database technology can also be done independently. So with each microservice persisting data to its individual data stores, the challenge comes when executing distributed transactions that span multiple microservices. How do you keep data consistent when these data are written, read, and stored separately? So one way to address this is with an event-driven architecture, and a common event-driven architectural pattern is known as a saga. So in a saga pattern, a service executes its logic, commits data to its local data store before emitting events for further processing downstream. This pattern repeats itself until all participant microservice has completed its required processing. And if we reimagine the earlier workflow as a saga, this is possibly one way of implementing it. As you can see, what used to be a single chain of synchronous transaction is now broken down into individual small transactions executed at a microservices level. So now the amount of information that we choose to include or exclude in an event becomes even more important because this has impacts on processing of downstream services. So if you think about event design, there are typically kind of two schools of thought. On one end, we have something called a sparse event. And a sparse event is designed by keeping information to a minimum, typically reserving that for the change that has happened. So if you take an example, we have, for example, order 123 that was created at 10:47 a.m. by customer 456. Notice how we keep that to absolutely essential information and omit anything else that do not require itself to be there. Conversely, we can also create events that are more like full state descriptions. And not only do we describe the change that has happened, but we go on to share current state information such as order status and total order value. And while sparse events are good to keep information to a minimum, there may not be sufficient meaningful data passed for consuming services to process their events. This will in turn drive a surge of lookup traffic to any required persistent data stores to get more context of the event, and this is generally an unnecessary or inefficient use of resources. But on the other hand, if we opt to deploy full state description, we may be passing too much information in events. This will cause a type of coupling known as semantic coupling. Downstream services becomes dependent on certain information provided by upstream services, and attempts to change it becomes difficult. Ideally, event schemas should be backwards compatible, and this means that new event schemas should still work for any consuming services of the event. And what happens when there's an error to a saga pattern? In a transaction that is distributed and span multiple microservices, we cannot simply roll back a transaction because the data has already been committed by microservice that has happened before the error. So we handle errors in saga patterns with a compensating event or compensating action event. A compensating event produces or indicates to participant microservice to reverse the effect of previously received events, and this can extend through the entirety of a saga. This will allow us to fully undo any past actions carried out by previous microservices. So say we run into an error where we have insufficient miles in our balance. A compensating event could be emitted that with the debit's failure status, and this directs, for example, the ticketing service to mark the ticket from pending to decline. Notice that we also chosen to show this as a decline status for auditing and tracking purposes, but there can be instances where the compensating event eliminates the data from the database itself. So if you look at implementing sagas in an application, we tend to see them being deployed in two ways. These are collectively known as the choreography-based saga and the orchestrator-based saga. In a choreography-based saga pattern, each participating microservice of the saga is pre-programmed to know what to do with each event it receives. Think of it as a dance routine where all the dancers know what moves to do when the music starts playing. The implementation logic of the saga is therefore decentralized, and each microservice has its own awareness of how the overall saga should run. To implement choreography-based saga, you need to ensure a backwards compatible event design to minimize any related forms of coupling. And choreography-based saga can be an easy choice to start a saga with. And it fits very well with the loosely coupled nature of teams who just want to focus on their microservice. But over time, due to the need to pre-program Saga logic into each microservice, this can become difficult to maintain as it scales. So to overcome some of the traditional challenges with choreography-based Saga, we can consider the use of Amazon EventBridge. Amazon EventBridge is a fully managed serverless event bus service, and one of its key functionalities is the ability to use event patterns as rules to trigger consuming services to process events. This allows us to offload routing logic of the Saga pattern to Amazon EventBridge itself and reduces the need to code in this logic into the microservice, thereby making a choreography-based Saga easier to maintain as it scales. So event rules basically trigger upon matching of certain event schema. And for our case, we can intentionally create an event schema that contains a type field. And by doing a string match of this field, Amazon EventBridge funnels the event into either the ticketing or customer service for processing. My co-speaker Marcella will dive into how this works in much greater detail. And an alternative to choreography-based Saga is actually the orchestrator-based Saga. And as the name suggests, orchestrator sagas have a central component or body that controls the flow of the saga and directs where each event should go. Orchestrator centralizes the logic of implementing the entire saga, making it easy for changes to be done in a single place. Some orchestrators can also support the ability to modify event data on the go, and this helps improve the integration and minimizes changes needed for microservices when joining a saga. Traditionally though, orchestrators themselves can become single points of failure and are difficult to scale. So to overcome some of the traditional challenges with orchestrators, we can consider the use of AWS Step Functions. AWS Step Functions is a fully managed serverless service that has built-in auto-scaling and resiliency that AWS manages on our customers' behalf. An orchestrator offers some unique advantage when it comes to event design. For instance, AWS Step Functions allow us to manipulate state data being passed from one service to another using something we call JSON paths. You can also make use of intrinsic functions, which allow us to perform basic data transformation on the state information as it's being passed. This will therefore help integration capability of different microservices and reduce the need to conform to a minimum contract. So to dive into deeper on how Amazon EventBridge and AWS Step Functions work, let me hand over the time to Marcella.
Hello, Justin. So thank you, Tong Sing, for giving us a high-level overview on event-driven architectures. So my name is Marcella. I'm a solutions architect looking after Asia emerging markets. So before I begin with today's discussion, can I just have a show of hands who have heard of Amazon EventBridge? Okay, come on stage, please. Okay, just kidding. Okay, so nice. So Amazon EventBridge is actually a fully managed serverless event bus and is focused on 4 main areas. But before I dive deeper into the 4 main areas, you might be wondering what exactly is an event bus. So event bus is simply a pipeline of events that makes it very easy for you to ingest and process your data. And the first part of EventBridge is actually your event source. So basically, where are you ingesting your data from? It can be from AWS services, it can be from your own bespoke customized applications, or it can be from your SaaS applications, for example, Salesforce, which is something that you're already using on a daily basis. And regardless of the event source, those events will actually land on an event bus. So let's say for your Amazon services, it will actually land on a default event bus. For your SaaS application, it will land on a partner event bus. And for your own customized bespoke applications, it will land on one-to-many customized event buses. And I also wanted to take this opportunity to talk about 2 add-on capabilities here. The first one is archiving. Mainly, it's actually the ability to archive your events and then use it later. So think about a scenario where you have an error on the go and you do not have the details of the event or you do not have the details of the error. So having this ability to actually record and replay your events is very useful in terms of any troubleshooting issues. And also, when it comes to actually any reconstructing changes to your application data, a sequence of events, this comes very handy as well. Or whether you're implementing any event sourcing architecture patterns as well, this will come very handy to you. And the other add-on capability that I want to talk about is actually schema discovery. So it's almost like having a blueprint of your event structure where you're able to store in your schema registry. So it's almost like having your own little library of your event structures where you can use on your current workflow or the workflows that you might have in the future. So it's almost like templatizations of all your event structure. And moving on to the third focus of Amazon EventBridge is actually rules. So previously, as I spoke about how different event sources land on different event buses, for example, AWS services will land on the default event bus. For your SaaS application, it will land on a partner event bus. Regardless of where these event sources land, we actually have the ability to create event rules that trigger different subscribers, which are AWS services, to handle and process these events. And let me show you how this works. So if you look at the screen, let's consider this sample event that you see. So this is an event that signals a creation of an order, and you can see in the fields important data such as order ID, order created timestamp, as well as order amount and the associated currency. And if you look on the right, it's actually an example of an EventBridge rule. So if you want to have a service, let's say for AWS Lambda, to process all of these orders that are created with a specific currency, let's say it can be AU, it can be New Zealand dollars, we can create a rule as such. So you notice how the structure of the event rule corresponds to the event itself, and how do you know it's a match? As you can see, the currency of the order contains AU. This actually triggers a match with one of the value under currency. So this is also known as an array match. So the whole intent here is that if your rule matches your event, then you're able to directly target your AWS service. So after your event matches your rule, we actually have a multitude of AWS services that process these events. It can be from your AWS Lambda, from your Amazon SNS, or even any third-party API destinations. So these are actually webhook type integrations that send to your events to any public interface endpoints. So this really opens up a wide range of integration capabilities and also have a built-in throttling as well as authentication capabilities, which makes Amazon EventBridge much more extensible as well as useful for your applications. So the main point here is that Amazon EventBridge is extremely useful when it comes to routing any complex routing requirements. And also when you're trying to directly target AWS services without any intermediaries or without any proxies. Okay, moving on to the next service which we will discuss today, it's AWS Step Functions. So also just a quick show of hands, who has heard of AWS Step Functions, who has pitched this service to your customers before? Okay, I won't ask you to come on stage. I don't see anyone raising up your hands. No worries. So today's session is for all of you to learn more about our serverless service as well. So moving on to the next AWS service we will discuss today is actually AWS Step Functions. So this service is actually extremely important and useful when it comes to building microservice architectures, because it really eliminates the need to manually orchestrate your application components as well as to manually define how they work. So AWS Step Function allows you to describe your workflows as state machines. So workflows such as failures, retries, service integration, as well as observability. So all this undifferentiated heavy lifting is actually taken care for you by AWS Step Functions, so that you and your developers can actually focus on what is core to your business. And like I mentioned, AWS Step Function allows you to describe workflows as state machines. And state machines are simply just a series of tasks where you're able to actually determine what is the sequence of your tasks, how do you handle failure and retries, in a way that's very tightly coupled to the business process that you're trying to achieve. And not to mention, you can also reuse the task for your current workflow or any workflows that you might have in the future. And you may wonder, what are some use cases of AWS Step Functions? It ranges from data processing, from IT and security automation, from machine learning training, as well as the main focus of today's discussion, which is microservice orchestration. So just to break down state machines, there are actually three main parts. Firstly is how do you define your state machines? And here in AWS, we define it through what we call ASL, which is Amazon State Languages. So ASL actually is very declarative in nature, and it's actually very similar to the JSON structure. So if you're very familiar with the JSON structure, then this should come very easy to you. And we also have it in YAML as well. So there are other means of defining state machines as well, such as AWS CDK, as well as Data Science SDK. So after you have defined your state machine, you can proceed to visualize it in our AWS console. So visualizing your state machine is actually extremely important because you can validate the correctness of your workflow, as well as effectively communicate your workflow to your business stakeholders of your organizations. So after you have defined and visualized your workflow, now it's time for you to execute and monitor your workflow. So when you execute your state machines, your execution will either come out successful or a failure. But regardless whether it's successful or a failure, all of these will be clearly logged. And when it comes to troubleshooting purposes, when it comes to auditing purposes, or any forensic purposes, I'll give you an example. For example, banking transactions or any workload that's very highly regulated, these will come extremely handy for you. And for those of you who can't wait to start coding in ASL, so if you take a look at the screen, let me break down the components of ASL. So what we have here is actually an ASL definition of a single state within a larger state machine. So this step is actually named as transcoding with callback, which is a part of a wider video imaging processing workflow which I've created previously. So the first one, if you look at components such as start, add, next, and end, so these are just positioning component, meaning where you are in your state machine workflow. And then there is state types, which in this case is a task state. And then moving on, we have resource. Basically, what is the service that is performing this task? And for this example, we are using AWS Lambda. And there's also this field called payload. If you notice on the screen, there's actually a lot of $sign. So we actually use JSON path, denoted by these $signs, to selectively manipulate your data that's passed into the state. And also there's different integration types. So meaning, how does your AWS Step Function integrate with your other AWS services? There are three main integration types. Firstly is request response, another one is wait for callback, and there is run a job. But for this example, we are using wait for callback. And lastly, we have retry logic. So retries in Step Function is particularly useful because you can fully customize the behavior of your retries within the Step Functions. And this is very independent of any native retries offered by the service itself, which you can use to full flexibility of your workload. And also there are going to be times where you want to do some basic and quick data manipulation or data transformation within your states. And with ASL, intrinsic functions, there's no need to call an additional service such as AWS Lambda to do all these basic tasks, such as generating UUID, any hash calculations, as well as any base 64 encode decode. So here in AWS, as you know, one of our leadership principles is invent and simplify. 95% of our services are actually built on customer feedbacks. So a lot of our customers actually tell us, is there a simpler way to build step functions? And this is exactly what we did. So last year in 2021, we actually launched the AWS Step Function Workflow Studio. So basically, it's a low-code studio for you to be able to build your step functions. You can drag and drop different service APIs. And there's also a built-in verification and validation and automatic code generations in this workflow studio as well. And like I mentioned, AWS Step Function really caters to a wide range of workloads. And it's very flexible to be able to adapt to different customers' use cases. And this is very evident in the amount of states that we have. We not only have one state, but 8 different kinds of states for you to customize your workflow. But today, I will just focus on 3 main states, which closely mirrors real-life business processes. So the first one is parallel. So a parallel state allows us to actually run separate workload logic concurrently to achieve different outcomes. So the collective results of a parallel state will determine what is your next step. So this parallel state really allows us to carry out different executions at the same time. And for map state, so map allows us to run different workflows repeatedly. So map state should be used whenever you have like a similar workflow that needs to be run repeatedly. And one way to use map state is actually we follow two models. One is the fan-out model and one is the scatter-gather model. And I'll give you an example. For example, if you want to send a message to different multiple destinations, then the fan-out map approach will be perfect for this situation. And lastly, we have choice. So this determines which state your state machine transitions to next. So let me give you a very simple example. For example, you're trying to increase the credit limit of your credit card. And using a choice state, your step function is able to actually make decisions based on the input state choice that you put inside. So for example, if the request that you make is higher than your pre-approved credit limit, then step function is able to send your customer's request to an automatic manager of sign-off approval. But let's say if your request is lower than a pre-approved credit limit, then step function is able to automatically approve this. So AWS Step Function really caters to a wide range of workloads, and like I mentioned, is so flexible that it's able to adapt to any customer's use cases. And these can be seen in terms of how Step Function integrates with other AWS services as well. We have not only just one, but two different types of integrations. You can either integrate with optimized integrations as well as SDK integrations. And in terms of integration patterns, we have not only one, but also three. Like I mentioned, we have request response, wait for callback, as well as run a job. So lastly, before I wrap up today's discussion, on a high level, I'll just describe these three integration patterns. And the first one is request response. So request response is when your step function calls a service and then progresses to the next state after getting a response. So these can work with both synchronous and asynchronous requests. And this is actually the default behavior for whenever you integrate an AWS step function with any AWS services. But what happens when your task actually takes a longer time to complete and it doesn't complete in a synchronous window? That's why AWS came up with two more integration patterns, which is run a job and wait for callback. So for run a job, your step function actually calls a service and waits for the job to complete. Right, like I mentioned, this is for cases when your tasks take a longer time to complete, and this works extremely well with integrated services such as Amazon Athena, Amazon SageMaker, as well as AWS Glue. Because these services are actually programmed to respond back to your step functions when your task is completed. And some examples of run a job would be actually batch processing jobs, data queries, as well as machine learning training. And lastly, for wait for callback, what happens is your step function actually calls a service with a task token. And only when your task is complete, then you return the task token. So this is also for use case scenarios when your task takes a longer period of time, when it doesn't complete in a synchronous window. And some examples of wait for callback can be for human approvals, can be for third-party integration, as well as working with any legacy systems. And when your task is complete, your task token will come back with a success or failure state. And then you can actually determine what is your next step of your business logic that you have. So with that, I'll hand over the time to Tong Seng, which will wrap up today's discussion.
Right. So thank you, Marcella. So here are some of the key takeaways I'd like to leave you guys with to summarize this session. So the first is to look for areas of improvement or areas of coupling between, not just between microservices, but also within an application. These are potential areas of improvement to reduce dependencies across components. Second, start to use Saga patterns today to ensure data consistency across multiple microservices and leverage Amazon EventBridge and AWS Step Functions to improve scalability and performance. So if you'd like to dive deeper into the concept of event-driven architectures, Saga patterns, and the like, here are some resources I'd like to recommend to you guys. We have AWS prescriptive guidance and AWS published blogs that talked about Saga patterns to greater detail. We also have, if you like to incorporate AWS Step Functions and Amazon EventBridge into your applications, a good place to start is in our AWS documentation. But if you also like to see these services in action, I would like you guys to check out the Serverless Espresso Workshop. The Serverless Espresso Workshop is a fully deployed virtual digital barista app that you can run on AWS and simulating a barista preparing a coffee. It starts using step functions to progress through the stages of coffee ordering to coffee preparation, payment, and then collection. So the Serverless Espresso Workshop is developed by our global serverless developer advocate team, and they are also behind something we call the Serverless LAN. Now, Serverless LAN is a one-stop shop website on anything serverless, from code snippets to architectural patterns to repeat podcasts or repeats of our serverless office hours, which is a live stream that happens every week on YouTube Live and Twitch. So if you like to, or you're very interested in generally about serverless here at AWS Singapore, I would like to recommend you guys checking out these sessions. Some of that has already happened, and you can check out the replays. But right here in this room, the next session is on USC 301, where my colleague Murthy will, who is over there, will go through how to employ AI ops in your serverless application to boost availability. So if you'd like to get certified on AWS certification, I would like to encourage you guys to check out Skills Builder. So with Skills Builder, you can make use of resources to prepare for more of our 11 certifications that span foundation, professional, and specialty levels. So scan one of the QR codes on the screen to get started. So thank you for the attention. Very happy to present this session with you today. And if you'd like to connect with us offline, here is our contact details, both email and LinkedIn. Thank you very much.